I welcome all of you to the class. As far as today's class is concerned, in today's class, we'll again do the problems for the calculation of stress. Okay, we'll do those problems which will help us in calculating the stress generated in the machine elements. And the problem I have selected is the problem, fundamental problem 17. The fundamental problem 17 says that we have a beam AC. Okay, the length or the span of the beam is 6 meter. This beam is being supported by two rods, rod AB and rod CD, such that the cross-sectional area of rod AB is 10 mm square and the cross-sectional area of rod CD is 15 mm square. This is what the question says. Okay, and this beam is being subjected to a triangularly distributed load. This is called triangular distribution of load because the shape of the load is in the form of a triangle. This is called triangularly distributed load. We have the triangularly distributed load on the beam. Okay, the load varies in the form of a triangle such that the intensity of load at this point is 0 and at the end C the intensity of the load is W. Fine. Now the question says that what determine the intensity W of the distributed load so that the average normal stress in each rod does not exceed 300 kilopascal. That is, under the whatever be the magnitude of this W, okay, the stress generated in rod AB and rod CD should not exceed 300 kilopascal. This is the condition that is given to us. Okay, that is, we have the rod AB and rod CD of cross-sectional area 10 mm square and 15 mm square respectively. And these rods AB and CD are supporting the beam AC. Fine. And this beam AC is being subjected to the triangularly distributed load having intensity 0 at end A and at end C having intensity W. Okay. Under the influence of this load W, fine, the stress generated in the rod AB as well as in the rod CD should not exceed 300 kilopascal. Fine. Then tell us how much is the value of this W. Fine. Now, in order to solve this question, let me draw the diagrams. So the question is like I will draw the diagrams. We have the rod AB. Oh, AC is the rod. It has a support here. Fine, let me draw the support like this. This is support AB. And at C, it does have a support, and support is like this. Let's call this a support CD. The total span of this beam is 6 meter. Fine. Okay. The cross-sectional area of this rod AB is 10 mm square and the cross-sectional area of end CD is 15 mm square. This is subjected to the triangularly distributed load, the acting downwards like this, having maximum intensity at this end equal to W. Okay. We have to calculate in each rod the stress should not exceed, I think, 300 kilopascal. The stress should not exceed 300 kPa. Stress generated in rod AB should be equal, stress generated in the rod CD should be equal 300 kilopascal. This is what is given to us. Okay, we have to find the value of W. How much is the value of this W? Okay, this is intensity of the load. Its unit will be kilonewton per meter. Okay, intensity of the load. Now we know. Let's draw the free body diagram. The free body diagram is our step number one. Our step number one will be free body diagram. Free body diagram. The free body diagram will be, this is 6 meter, beam of span 6 meter. Okay, now it is being subjected to triangularly distributed load, and we know from our fundamentals of mechanics that a triangularly distributed load or any other load distribution on a beam or any other machine element can be represented in terms of a single force, whose magnitude will be equal to the area of the load diagram. Okay, that is, we'll be replacing this triangular distributed load by a single concentrated load, such that the intensity of the load will be equal, the magnitude of that load will be equal to the area of the diagram, and the area of the diagram is half of base, that is 6 meter, multiplied by the perpendicular, that is equal W. So we'll write this as one half of 6 meter into W, and the unit of W, we say it is kilonewton per meter. So meter and meter will cancel. So it will be 3W kilonewton is the force. And where this force will be acting, we know the force will be acting at the centroid. The force is to be placed. This is what we have done in our basic fundamentals of mechanics. The force will be acting at the centroid. And we know for a right angle triangle, from this 90-degree side, the the centroid position is, the centroid lies at 1/3 of the base, that is 1/3 of 6 meter, that's equal 2 meter. We know that the centroid lies at a distance of what we had calculated as b by 3. Our base is 6, so it will be 1/3 of 6, that is 2 meter. So from here we'll go to a distance of 2 meter and we'll apply this load, that is 3W kilonewton. Load is acting downwards, okay, such that this distance will be 4 meters. This distance is 4 meter. Okay, this distance will be 2 meter. This is fine. Now, after doing this much, so we have replaced this triangularly distributed load. Now, this triangular distributed load will try to move the beam downwards, and the reaction will be offered by the reaction forces created in the rod AB and the rod CD. Okay, and the reaction will be upwards. Fine. So we'll be having reaction force upward. Let's call this as reaction AB, RAB. And at this end, we'll be having reaction upwards. Let's call that as RCD, reaction RCD. Fine. These will be the reactions upwards, which will try to prevent the beam from going downwards. Fine. Now we'll write, after drawing the free body diagram, our step number 2 is writing the equations of equilibrium. Okay, this is our end A, and I know this is my end C. What can be the equations of equilibrium? This is quite understandable, that we can write RAB, this is force acting upwards, let's take this as positive, plus RCD, and minus 3W should be equal to 0. All the units will be in kilonewton. Fine. Therefore, RAB plus RCD is equal 3 times W. Let's call this as equation number 1. Fine. Since we know from the fundamentals of mechanics that equations of equilibrium does not mean the summation of forces will be equal to 0. Equilibrium does mean that the summation of all the moments at all the points should be equal 0. Let's select point A. At point A, summation of all the moments about an axis passing through point A should be equal to 0 for equilibrium purpose. That's what I have been, exaggerating from previous classes, that we have to assume an axis passing through point A. All summation of all the moments about an axis passing through point A should be equal to 0. This is even true for an axis passing through point C, or through an axis passing through any point. Okay. Now what it can be? Let's take the moments about an axis passing through point A. First moment will be because of 3 kilonewton force, 3W kilonewton, and this is trying to move the beam in the clockwise direction. Okay, it's trying to rotate the beam in the clockwise direction. We'll be taking the clockwise moment as negative. Therefore, it will be 3W, this is force, multiplied by the force arm, that is 4 meter. Fine, but it will be minus because because it's trying to rotate the beam in the clockwise direction. Fine, plus the moment because of RCD, it's trying to rotate the beam in the anti-clockwise direction. Let's take it as positive. It will be RCD multiplied by 6. Okay, has to be equal to 0. Fine. So this means RCD becomes equal 12W divided by 6. Fine. That's equal to W. Let's call this as equation 2. From equation 1 and equation 2, okay, we can write RAB plus RCD. In place of RCD, we'll write 2W has to be equal 3 times W. That is RAB becomes equal 3W minus W is equal W. This is the value of RAB. Let's call this as equation 3. Okay. This is fine with us. This is in kilonewton, meter, fine. Okay. Now, we know now the force in RAB is W and force in RCD is 2 times W. Fine. Let me now calculate the stresses. As far as the stresses are concerned, let me clean some space first. We can therefore write it as therefore in the rod AB, okay, we have rod AB is say like this. Okay, this is A, this is B. The force in rod AB is acting in this direction, that what we call as RAB. Since this force is perpendicular to the area, okay, therefore the stress that this RAB will cause will be the normal stress, okay, from the definition. Therefore, normal stress in the rod AB is equal force in the rod AB, that is RAB, divided by area of the rod AB, that is area of the rod AB. Fine. That's equal RAB is equal W divided by area of the rod AB is 10 mm square. That is 10 mm square. It is given to us. And this is given to us that stress in the rod AB should be equal 300 kilopascal. That is 300 kPa. Okay. Which implies W divided by 10 mm square is equal 300 into 1000 kilopascal. Yes, that means Newton per meter square. Okay, why we are writing this? Because Pascal is Newton per meter square, kilo is 1000. Fine. We can further write this as, now we have to simply solve it. We can therefore write this as W divided by 10. Okay. By the way, if you look at this W, okay, what is the unit of this W? From the previous equations, like here, the unit of this W we had stated it is kilonewton. Okay, it's kilonewton, RAB, RCD. So you can also write a kilonewton here. This is W kilonewton. Keep units, okay, close by. Okay, write every term with its corresponding units. Fine, because you look here, you have W in terms of kilonewton, 3W kilonewton. So you will get RAB, RCD, all everything in terms of this kilonewton. Fine, so it will be kilonewton. Okay, so it is W kilonewton, W into 1000 Newton, okay, divided by 10 mm square is equal 300 into 1000 Newton divided by meter square. We know 1 meter is equal 10 raised power 3 mm, so it will be 10 raised power 6 mm square. Fine. So 1000 and 1000 will cancel, Newton and Newton will cancel, mm square and mm square will cancel. Therefore, W will be equal 3000 multiplied by 10 into 10 raised power minus 6. Okay, in terms of kilonewton, that's equal, okay, that will be equal 3 into 10 raised to power 4 into 10 raised power minus 6. That's equal uh, 3 into 10 raised power minus 2. Okay,
Sir,
this
ये
is W.
300 है ना, 3000 नहीं है ना?
So we have a little correction here. This is 300. Okay, so it will be, then W will come out to be equal, W will be 300 into 10, that is 300 into 10 into 10 raised power minus 6, that is 300 into 10 raised power minus 5, which can also be written as 3 into 10 raised power minus 3. Fine. So as far as our W is concerned, from this equation, from sigma AB, the value of W becomes equal, since the unit of W is what? W we have taken in kilonewton. Okay. W in kilonewton, I will write here, W in kilonewton will be equal 3 into 10 raised to power minus 3 kilonewton, that is equal 3 Newton is the value of this W. Fine. This is the value of this W when we are taking sigma AB. Now let's recheck it. What we will do, let's talk about the stress in the rod CD. If we talk about the stress in the rod CD, what it will be, stress in the rod CD will be, stress in the rod CD is equal reaction in the rod CD divided by area of the rod CD. Reaction in the rod CD is equal to W kilonewton divided by area of the rod, that is 15 mm square, and it is given to us it should not exceed 300 kilopascal. Fine. What does that mean? That means it should be 2W into 10 raised to power 3 Newton divided by 15 mm square should be equal 300 into 1000 Newton per meter square. I will write this as 10 raised power 6 mm square. Fine. So 1000 Newton will cancel, mm square will cancel. So my W will become equal 300 into 15 into 10 raised power minus 6 divided by 2. Okay, that is equal 15 into 300 is 4500 divided by 2, it is 2250. It is 2250 into 10 raised to power minus 6, which is equal, you can write this as 2.25 into 10 raised to power minus 3. Since we know, therefore, the value of W from this formula becomes What does the value of W from this formula become? The value of W becomes equal 2.25 into 10 raised power minus 3, and we have W in terms of kilonewton. That is, W is equal to how much? 2.25 Newton. Okay. Now look into the two values of W. We are having now two values of W. Okay. When we calculate stress in the rod AB, the value of the W should not exceed 3 kilonewton. Okay. When we calculate stress in the rod CD, the value of the W should not exceed 2.25 kilonewton. Now, what value of W we will apply on the beam? Should we apply a load of 2.25 or we should apply a load of 3 kilonewton? I will say we should not apply a load of 3 kilonewton. W should not be equal to 3 kilonewton, 3 Newton. You know why? Because if you place W equal to 3 Newton, okay, at this value of W equal to 3 Newton, the value of the stress that will be generated in the rod CD will be greater than 300 kilopascal. This is quite easy to understand. The reason is when we calculated the stress generated in the rod, for the stress generated in the rod equal to 300 kPa, what should be the value of the W? The value of the W came out to be equal to 2.5. So when the value of W is 2.25, when the value of the W is 2.25, at that time the stress in the rod CD will be how much? 300 kPa. If we have, if we increase the value of W and place it, say for example, 3 Newton, what will happen? The value of the stress generated in the rod CD will exceed 300 kilopascal, which rod CD will not be able to will not be able to what we say withstand. Okay, so it is possible that the rod CD will break. Okay, so the stress generated in the rod CD puts up a restriction on us that what value of W we should select. Should we take W equal to 3 Newton or we should say W equal to 2.25? We should say that the value of W should be equal to 2.25. If we have W equal to 3, then the stress in the rod AB will be equal to 300 kilopascal, but the stress in the rod CD will be more than 300 kilopascal. So this is how these questions are meant to be solved, by drawing the free body diagram, writing the equations of equilibrium, and giving the definition of the stress, that stress is equal to force divided by area. Thank you very much.